In the two examples of the previous section, we examined springs that experience significant deformation. To what extent do cables and bars exhibit spring-like behavior? In statics, we assume structural elements are rigid with the exception of springs. This is the same as saying that non-spring structural elements are infinitely stiff. We now take some time to examine the validity of this assumption. To do so, we need to look ahead to mechanics of materials and examine a standard experimental test employed to determine stiffness-related material properties, the tensile test. A tensile test involves the insertion of a standard coupon of material into a machine that stretches the coupon and records the force required to do so. In this way, we can determine the actual finite stiffness of the material. This figure shows the standard coupon, a cylindrical specimen with threaded ends that can be securely fashioned to the jaws of the tensile testing machine. When the machine is activated, it moves the jaws apart at a constant rate, and the force required to do so is recorded. It turns out that material stiffness is not correlated with force versus displacement as it is with stress versus strain. We use the Greek symbol lowercase sigma to indicate stress, and that's force per unit area, where the area would be the cross-sectional area of this coupon. So looking at it from this position, we would just see the cross-section of the cylindrical specimen. Strain is designated with the lowercase Greek symbol epsilon, and that is the stretch normalized to the initial length of the specimen. When stress is plotted versus strain, a typical result for a steel coupon and an aluminum coupon are shown here. Important aspects of these test results are as follows. First, material behavior varies widely among all classes of materials. What we see here is representative of a ductile metal. The word ductile is synonymous with energy absorption. The fact that the specimen experiences significant deformation before it breaks is an indication of that energy absorption. A material that absorbs relatively little energy before breaking is a brittle material. A glass or ceramic would typically fall into this category. Brittle materials can often take significant load, but then fracture suddenly with little warning as they approach their limit loads. Most of our applications are going to be in structural materials, and we like to avoid brittle loads, so the ductile materials are the most appropriate for us to examine. For these ductile metals, there is a range of stress and strain at low strain where there is a linear relationship between stress and strain. This is where we want to operate in any structural engineering capacity. This range is also said to be elastic, which is to say the deformation is reversible. If we load the material within this range and then unload it, the material retreats along the stress-strain curve and no permanent deformation occurs. With respect to the steel, for instance, I'll use these arrows to indicate I'm climbing up the stress-strain curve as I increase the load, and let's suppose we increase to this point. If I then unload it, I'll come right back down this stress-strain curve and go back to both zero load and zero deformation. This is the desirable operating space for any structural engineering application. The threshold between the reversible and the irreversible domains is indicated by this symbol sigma y, which is a yield stress. For both the steel and aluminum, this is on the order of tens of thousands of pounds per square inch. For steel, this is on the order of 36,000 pounds per square inch. And it will turn out if we convert that into SI units, that's about 250 MPa, megapascals. If we increase the load on the material beyond its elastic range, that is, above the yield stress, permanent irreversible deformation occurs. It is observed experimentally that if we impose a stress or strain beyond this elastic limit and then unload it, the specimen unloads elastically. That is, it unloads along a line parallel to its linear elastic response, leaving a permanent deformation when it's completely unloaded. Suppose, for example, that we were going to impose a stress at this level above the yield stress. As we load this up, it would climb this stress-strain curve to this position. And now when we unload it, we have an elastic unloading. We have a slope parallel to the elastic range. And when we unload it, we come down the curve this way. In this case, when we get back to zero load, we now have a permanent, irreversible deformation. We can define a property from this stress-strain curve that tells us something quantitative about the rigidity or stiffness of the material. We define an elastic modulus E to be the ratio of the yield stress to the yield strain. For the steel, based on the numbers that we can see on the left part of the figure, this would be 36 times 10 to the third pounds per square inch over a strain at yield of 0.0012, and that number turns out to be about 30 million or mega pounds per square inch. And if we convert that to our SI units, that turns out to be about 200 gigapascal. For the aluminum, the same calculation gives a modulus about 1/3 that of steel, on the order of 10 million pounds per square inch, or 70 GPa, 70 gigapascals. Note that these numbers are representative. The actual value for a particular steel or aluminum alloy depends on its exact composition and its method of fabrication. Within the linear elastic range, we have that stress is proportional to strain through this elastic modulus. And now if we think about the definitions for stress and strain, stress is a force per unit area, and strain is a stretch normalized to the initial length. What that means is we can write a relationship between force and stretch that looks like our spring relationship, with spring constant K equal to the initial cross-sectional area times the elastic modulus over the initial length. The spring constant has both a geometric component, that is a ratio of cross-sectional area to length, and a material component in the elastic modulus. The stiffest structural element is therefore short and squat, so it has a high ratio of cross-sectional area to length and is fabricated from a stiff material. It has a large elastic modulus. Let's return now to one of our earlier examples from section 3.1. You'll note in these figures that we've made a distinction between the angles that elements make with the horizontal before and after the loads are applied. So instead of having 30 degrees when the loads are applied, the angle element AB makes with the horizontal is labeled alpha, and instead of 45 degrees, the angle bar AB makes with the horizontal is labeled beta. So the question we want to ask is, how much difference is there between alpha and 30 degrees and beta and 45 degrees with the kinds of structures that we're likely to look at, made out of the kind of materials that we're likely to use? Without making a distinction between the geometry before and after loads are applied, we found previously, employing particle equilibrium at A, that member AC carries a compressive load of about 90 newtons. We didn't specify any dimensions for AB or AC in that problem, but let's suppose that AC has a length of 1 meter and is a solid cylindrical steel bar of diameter 1 centimeter. How much does it actually shrink under that 90 Newton load? So let's calculate a K. Based on our assumptions, we have initial cross-sectional area times elastic modulus over length. And we said we were going to take the steel bar as having a diameter of 1 centimeter, so the cross-sectional area is pi over 4 times 0.01 meters squared. And for a steel, a representative modulus is 200 gigapascals, or 200 times 10 to the 9th newtons per meter squared. And then we're dividing all that by the length, which we said we would take as 1 meter. And when we calculate that spring constant, it's 1.57 times 10 to the 7th Newton per meter, or 15.7 million newtons, meganewtons per meter. The corresponding contraction in AC is the force over K, and with a load of 90 newtons and this value of K, we end up with 5.73 times 10 to the minus 6th meters, or 5.73 microns. Granted that our load is very modest, but that's a really small contraction. If the load were, say, 10 kilonewtons, 10,000 newtons, the deflection would be about 0.6 millimeters in a structural element of length 1 meter. This tells us that in most structural engineering problems, the rigid body assumption is an excellent approximation of the extremely stiff reality. The bottom line is that we can also model bars and cables as very stiff springs. This becomes useful in statically indeterminate problems where the movement of a joint from its undeformed to its deformed position implies a certain amount of stretch or contraction in members attached to the joint, which in turn tells us how much load those members are carrying. As a reminder, a statically determinate structure is one in which the loads carried by the members can be determined solely from the equations of static equilibrium. In this case, the number of structural elements, that is, the number of unknown forces, matches the number of component equilibrium equations. In contrast, a statically indeterminate structure has more unknowns than equilibrium equations, and usually none of the unknowns can be determined on the basis of static equilibrium alone. As an example, we have two different two-dimensional assemblies. The one on the left, we have 2 ropes and a single 2,000-pound force applied at the ring at A. If we were to draw a free body diagram of the ring at A, we would have 2 unknown forces in cables AB and AC. We would have 2 scalar equilibrium equations, and we would be able to solve that equation for the forces carried by those 2 ropes. On the right, when we draw the free body diagram, we're going to have 3 unknowns. So on the basis of static equilibrium, we don't have enough information. We've got 2 scalar component equations and 3 unknowns. But let's consider now another possibility. We know the application of the force will stretch the cables and cause ring A to move to a new location. I'll draw this as very exaggerated so that we can see the movement, but let us suppose that application of this load resulted in a displacement in the x direction, which I'll call U sub A, and then separately we have a displacement in the vertical direction, which I'll call V sub A. Again, I'm showing these greatly exaggerated, but just so that we can see that there's a deformed location and an undeformed location. As A reaches a new location, we can calculate the stretch of each rope, delta AB, delta AC, and delta AD. Knowing the material properties, that is, the modulus of elasticity, and the cross-sectional areas of each rope, we can calculate a spring constant for each and find the force carried by each rope as FAB equals KAB delta AB, and similarly we can find FAC equals KAC delta AC, and FAD equals KAD delta AD. We can then ask if those forces obey the component equilibrium equations. If yes, we have our solution. If no, we reposition the displacements u and v so that the member forces do satisfy equilibrium. In effect, we have changed our fundamental unknowns from the forces carried by the members to the new coordinates of ring A. This process works whether there are 3, 4, or more structural elements supporting A. When the deflections of A are small, there is a process for finding the deflections of A that involves solving a set of linear equations so that we don't have to guess the new position of A or use some tedious nonlinear approach to solving the problem. These techniques, however, are the province of mechanics of materials, so we'll leave the details of the solution techniques to a future class. For now, it is enough to be able to classify problems as statically determinate or statically indeterminate, and to recognize that the equations of static equilibrium are no less valid in a statically indeterminate problem. The equilibrium equations must be supplemented by so-called compatibility relationships, that is, force-displacement relationships like F equals K delta, in order to find a solution in statically indeterminate problems. Let's now try a couple of spring problems, and then we'll return to particle equilibrium and examine some three-dimensional problems.